right, integration using the substitution rule. That's what we're going to do. We're going to go through 4 examples, and then you're going to get a hang of how the substitution rule applies to any of these questions. All right, first thing, once you see an integrand, which is the value inside, you notice that one of the term is kind of a derivative of the other term. So in here, we set u equals to 1 plus x squared. And once we have that, we're going to take the derivative of both sides. So du is equal to 2x dx, because that's the derivative. Derivative of 1 is 0. And what we want, notice that in the original, we have a 2x here, we have a dx there. So use this in place of 2x dx and go ahead and change this integration into function of u. Let me rewrite this better so that you can see that 1 plus x squared times 2x dx. That's the first step. And now it's very straightforward, and we go to indefinite integral of square root of u times du, because du is 2x dx. Simple as that. And now we're going to go ahead and change that to the exponential form. So integration of u to the half du. And what is that? Well, that is 2/3 u to the 3 half. And then once we have this, we're just going to go ahead and substitute back what u was, and that is 2 times 1 plus x squared to the 3 half, all over 3. And you can leave it alone like that, or you can actually simplify it more, and that becomes 2 times square root of 1 plus x squared, 3 all over 3. And that's basically it. I mean, yes, you can go and simplify it more, but this is as good. And the last step, 2 times 1 plus x squared times square root of 1 plus x squared all over 3. That is the final answer. And don't forget plus c, the constant of integration, because of its indefinite integrals. And if you want to check, you can go ahead and check by differentiating that function. And if when you do this, you should get this back. Okay, that's what you can do. All right, let's look at another example. Okay, we got this one. So let's change that to the exponential first, to the half dx, and in this case we let u be 3x plus 4. So take the derivative, du is equal to 3 dx. Very good. Du equal to 3 dx, and then when you go back to the original integration, the integrand, notice that we have dx in here that needs to be replaced by du. So we need to solve this equation, du equal to 3 dx for dx. So when you do that, you get dx equals to du divided by 3. Excellent. Now we're going to go back, and then we're going to replace this. So we have, here we go, integration of u to the half times du divided by 3. And we're going to simplify that more, 1/3 integration of u to the half du. Okay, and now once we have this, we can go ahead and solve. Okay, let's do the integration. 1/3, this would be u to the 3 half divided by 3 half. We're going to deal with that fraction later. And then plus c, the fraction, that would be 2/3 u to the 3 half. Simplify. We get 2/9 u to the 3 half plus c. I should have said plus c there. Okay, and now we're going to go ahead and substitute what u was. So the final answer here is 2/9. U was 3x plus 4 to the 2/3 plus c. Here it is. That's the final answer for that. And then we use the substitution method. Excellent. You can change that to the radical form if you wish, but you don't need to, but you can if you want to. Okay. Okay, let's look at this question. This is, we're going to do integration of x cubed times cos of x to the fourth plus 2 dx. And there is a table of integration that you will be given to. And I just went through and just wrote down two of the basic ones. There are like 5, 6 of them, especially for trigonometry. As same as the differentiation that we did, if you remember that. All the differentials for the trigs, they have their own formulas. All right, so we're going to use these, okay? But the idea is the same for the substitution method. So the first thing is that you look at the inside this, and you notice that, the x to the fourth, the derivative of x to the fourth is 4x cubed. That x cubed is right here. So that's a clue. So go ahead and say u equals to x to the fourth plus 2. Okay, and then you take the derivative of both sides. Du equals to 4x cubed dx. The derivative of 2 is 0. And now you notice that you got x cubed here, you have a dx there, and we have an x cubed here and dx there. So we can solve for x cubed dx. So that would be du divided by 4 equals to x cubed dx. Very nice. Now we're going to go ahead and replace what we see here with u and du. So let's rewrite. This is integration of the cos of, it would be cos of u, and then for x cubed dx, which is right up there, x cubed dx, we're going to put du divided by 4. So that's du divided by 4. Okay? And that, I'm just going to remove the constants. Remember one of the properties of integrals? That's cos of u du. And now we're going to go ahead and do the integration. So what do we have? 1/4 cos of u, which is the integration of cosine is sine. So it would be 1/4 sine of u, and then plus c. We have to add the constant of integration. And then the last step is you're just going to go back there and replace what u was. 1/4, and then in this case will be sine of x to the fourth plus 2, and then plus c. And that is the final answer. If you take the derivative of this, you will end up getting this original, the differentials, which is x cubed times cos of x to the fourth plus 2 dx. All right, now let's do another one, the last question. Here it is, last question. All right, so in this case, we're going to do the same thing, but remember again, notice that the bottom x cubed and x squared are related. Okay, the differentials of x cubed is 3x squared. Oh, we got the x squared again, and that means you can just simply set u equals to 2 plus x cubed. And then once you have that, you can go ahead and take the derivative and then solve for dx, because the only thing we have here on this side is x squared dx, these two together. So that's what we want. So du divided by 3 equals to x squared dx. Excellent. Now let's go ahead and rewrite. So the first thing we're going to do, we're going to change the radical form to the exponential form, which is right there. And then we're just going to rewrite it x squared times dx. And now we're going to go ahead and do the substitution. So this would be the integration of u to the negative half times du. Okay. And now that we have this, we do go ahead and do the integration. Oh, by the way, this is du over 3. Apologies, du over 3, which is right here. Okay. And now that we have that, so 1/3 outside, and then u to the negative half plus 1 over negative half plus 1. I know I shouldn't be doing that now, because by this time you already know exactly what to do, but that's okay. For some of us need a review, I'm going to do that. And then plus c, and then once we have that, we're going to go ahead and punish. So let's go ahead, and then we do the substitution, and that would be your final answer. Excellent. Now, if you want to check, again, you can go ahead and differentiate. Okay, differentiate this, and you should get your differentials back, which is this right here, the x squared over square root of 2 plus x cubed. And for simplicity's sake, actually, for the good practice, let's do that. Okay, let's differentiate this. We have to use our chain rule. So first of all, we have 1/2. There's a 2/3 outside. So we get 1/2 times 2 plus x cubed. So we got to deal with that. To the power of negative 1/2 times the derivative of 3 x to the 3, which is 3 times x squared. All right, so now let's do the math on that. You notice that the 2 and this bracket misplaced, they should be front. So the 2 and a 2 divide, and then the 3 and a 3 divide. So what you will have is x squared, which is right here, times plus x cubed to the negative 1/2, which is equal to x squared over the square root. That's negative 1/2, means you drop down to the denominator, and then the square root of 2 plus x to the 3. That is our original differentials that we got, okay, which is right there. All right, excellent. Until next time, make sure you check out the next video. I'm going to focus mostly on the trig, integration of the trig functions. All right.